Hello, everyone. We're about to get started with the webinar here. I'm Dan Rutherford, Senior Director of Research at the ICCT. Thank you very much for attending today's webinar. We're very excited to present ICCT's updated Net Zero Aviation Roadmap for you today. Before we start with our presentation, a few housekeeping items. First, this webinar is being recorded. We will also make it available on our YouTube channel in the coming days. Second, everyone on the webinar currently has their microphones on mute. If you have questions, you can write them in the Q&A in the control panel. After the presentations and panelist remarks, which will take about 30 minutes, we'll spend the rest of the time answering questions from the audience. Again, today we are discussing the update to ICCT's Net Zero Aviation Roadmap. We have three excellent presenters for you today. First up is Sola Zheng, Senior Researcher at the ICCT and the lead author of the study. After that, we'll hear some remarks from Jayant Mukhopadhyay, Senior Researcher at the ICCT, who leads our contrails mitigation work. And then finally, we will hear some remarks from Supraja Kumar, Associate Researcher also at the ICCT. Supraja leads our work on other short-lived climate pollutants, including nitrogen oxides and fine particulate matter. So again, thank you all for being here. I'll now turn things over to Sola to run us through this study design, findings, and policy conclusions.
Thank you, Dan. I will now walk you through the background, methods, and key results from our newly released Aviation Vision 2050 report, focusing on the potential for climate neutral growth through non-CO2 control. So first of all, let's go back 3 years in time when the net zero CO2 by 2050 goal was first introduced at the 41st Assembly of the International Civil Aviation Organization, or ICAO. And that is also the year when a lot of groups, including ICCT, developed global decarbonization roadmaps for aviation. On the right side of the slide, you will see IATA's compilation of major roadmaps, where the dark green and light green bars represent BioSAF and eSAF. So you can see that there is an overwhelming consensus that SAF is the most critical mitigation technology, at least in the CO2 space, and then it's on average half of the reductions in all the roadmaps. It's followed by fuel efficiency improvements on both airframes and operational activities at 30% of the total reductions. And there are also smaller technology levers like zero emission planes and carbon removal technologies, as well as economic instruments like carbon pricing that will result in demand response. Those will all contribute to a net zero CO2 goal as well. However, it's been 3 years since 2022, and the progress towards a net zero goal has been quite slow. Specifically, in late 2024, we assessed how the different mitigation technologies are tracking towards our modeled scenarios in the first Aviation Vision 2050 roadmap. And our conclusion is that for all of the mitigation levers, it's on track to our action scenario, which is the red line in the graph. And then you will notice that there's barely any CO2 reductions in 2050 compared to 2025 in that particular scenario. So even though it's a great improvement from business as usual, there's a long way to go to reach the net zero pathway that's in blue in the graph. So this slow progress towards the net zero goal is one of the two main motivations behind this updated roadmap. The other main motivation for this update is that there is a growing amount of evidence of how now CO2 climate impacts from aviation is at least the same magnitude as the CO2 impacts from aviation. But then there is also a lot of evidence that there are technologies that can help us reduce these non-CO2 impacts in the near term. And then these technology potential is really linked to the characteristics of non-CO2 pollutants. In this report, we really dive into the differences of mitigation potentials between greenhouse gases, which are carbon dioxide, methane, and nitrous oxides for the aviation sector. These pollutants, they last 10 to thousands of years in the atmosphere, and then the cumulative amount of these pollutants really matter. But in contrast, there are a variety of short-lived climate pollutants from aviation, notably contrails and not nitrogen oxides. They only last hours to days in atmosphere, which means once you're able to reduce the emissions of these pollutants, the warming impacts of them also will stop pretty instantly. Therefore, we really see this as an opportunity to complement the CO2 reduction technologies that I just described. And we designed this study to answer this specific question which is how can cuts to short-lived climate pollutants from aviation contribute to the sector's alignment with Paris Agreement? And I will now dive into the high-level methods that were used in this year-long study. We really upgraded all aspects of our modeling capabilities for this new roadmap. We first developed a new 2023 global flight emissions inventory, which serves as the basis of our emissions projection model called PACE. And then the PACE model outputs future emissions from 2023 to 2050 in mass, as well as in effective radiative forcing for contrail cirrus specifically. These emissions were then fed through a simplified climate model called FAIR, and the FAIR model calculates how much aviation contributes to global temperature change. So a little bit more details on the base inventory. The biggest update and improvement is that we are using ADS-B real world flight trajectories data as the basis of our modeling. This not only allows us to can incorporate more accurate flight distances, but also really enables contrail modeling, which needs information on how aircraft are interacting with the meteorology at a given time and day of the year. And we use the BADA 3 aircraft performance model developed by Eurocontrol for the fuel burn and emissions, as well as a Python implementation of the control series prediction model, or COSIP, for the modeling of the per flight emission performances. There are also detailed engine emissions being modeled through known methods from existing literature. And on the right side, you will see a snapshot of the average amount of contrail being emitted in 2023. As many of you may already heard, contrail is a very geographically concentrated issue. And you can also see on this map that there's a really big hotspot in the North Atlantic airways concerning US and the EU, because of how dense the air traffic is in that region, but also how the atmosphere pockets tend to be colder and more humid in this particular part of the globe. There's another hotspot in the Southeast Asia region as well. And then I'll come back to how this informs our design of the mitigation scenarios. So speaking of the future emission scenarios, we designed 5 scenarios where 2 of them represent a business as usual type situation. One of them is historical trends, where we model no action on aviation emissions reduction whatsoever. The other one is called current commitments, which encompasses announced SAF mandates and manufacturer goals for designing more fuel efficient aircraft. And then we have 3 scenarios that focuses on one of them focuses on maximum GHG reduction. The other one focuses on maximum SLCP mitigation. And the full breakthrough scenario is the combination of the two scenarios above to represent the highest ambition scenario in our model. And within these scenarios, there are different levels of technology uptake being incorporated. And on the uh, greenhouse gas side, it's the same three main mitigation levers: fuel efficiency, SAF, and SAP. And there's a lot of new work that went into the short-lived climate pollutant side of mitigation. For the first one being the gradual introduction of leaner engines, which have lower NOx and MEPM emissions into the existing fleet over time, and followed by control avoidance, which is the technology where we can reroute flights to avoid atmospheric pockets that are prone to persistent control formation. And then in addition to leaner engines and avoidance, there are two types of low aromatic fuels that we're modeling. One is hydrotreated fossil jet A. The other one is sustainable aviation fuels. And then they both reduce contrail through the same mechanism where the lower VPM emissions due to the lower aromatics in the fuel will reduce the amount of ice particle being formed at the exhaust of the aircraft. And lastly, we continue to model a small economic lever where there is going to be demand response to increased fuel cost, which is also interpreted as a carbon pricing in our model. So my colleagues will dive into some of these technologies in more detail later as well. I will now jump to some high-level results from the modeling. So first of all, if we look at the greenhouse gas side of things, we will see that the announced SAF mandates in four geographies, which are UK, EU, Japan, Brazil, they add up to about 10% SAF blending in 2050, which is quite moderate. And then we also model a much more optimistic scenario of 70% SAF blending in 2050. We did not go to 100% blending because of how the current uptake of SAF has been rather slow, and we're not on track to achieve that ambitious of a level of SAF blending. And then because of the more like not as kind of aggressive SAF uptake, we're seeing that even in the greenhouse in the GHG forward scenario and the full breakthrough scenario, which are the green lines in this graph on the right, there's still going to be 500 million tons of residual CO2 equivalent emissions in 2050, and that puts aviation kind of above its current share of the remaining climate budget of 4%. And this is this is giving us the basis of kind of of evaluating how non-CO2 mitigations can help to bridge the gap towards a well below 2 degree compatible pathway. And for the SLCP mitigation, we want to briefly walk you through a few of the mitigation levers. One is how hydrotreating is modeled. So the hydrotreatment really will peak at 80% of the global energy demand in the SLCP forward scenario because there is not a lot of SAF in the system, and then that is assumed to be implemented in all of the flights departing from high income and the middle income countries, but not low income countries. In the full breakthrough scenario, the hydrotreated Jet A will peak around 60% of the global energy demand in the late 2030s, and it will be overtaken by SAF ramp up in the later years. And then they combined their zeroing out the conventional fossil Jet A and delivering a significant amount of contrail and other SLCP benefits. And then in addition to the deployment of alternative fuels, as I mentioned, control avoidance is also a key lever for reducing contrails from aircraft. And we are modeling a staggered implementation of the rerouting technology that based on the income level of the countries. And then you can see on the graph on the left that it ramps up starting around 2030 for high income countries and reaching 95% of effective avoidance around 2043. And it's delayed by 10 years for upper middle income countries. Even though this seems like a very aggressive pace of scale up for the avoidance technologies, it is important to remember that the control formation is very concentrated on a subset of the global flights. So specifically to avoid, if we were able to reroute 10% of the flights in the world, we will already achieve a 90% reduction in contrails. So it's the high percentages being modeled here is not it does not imply a really large shift in all of the routing behaviors in the global flights. And on the graph on the right, you will notice that so as a result of avoidance, the SLCP forward and full breakthrough scenario will achieve a significant level of control reduction at about 93% of reduction compared to historical trends. But you will also notice that even for GHG forward scenario, which is the yellow line, there is some substantial mitigation in contrails. This is due to the amount of SAF in the system, where 70% of 70% SAF blending will lead to about 30% reduction in contrails. And then there's also operational improvements where we can transport the same amount of people and goods with fewer flight kilometers flown, and that also very effectively reduces contrails. So with the implementation of the aforementioned mitigation levers, we now move on to assess how the total amount of warming from aviation will be in the 5 scenarios that we modeled compared to the historical warming up to 2025, which is 0.058 degrees Celsius. And then we also sometimes refer to it in the millidegree space, which is 58 millidegrees. And you can see that in the historical trends and current commitment scenarios where minimal actions are taken to reduce aviation emissions, we are on track to double the historical warming in 2050 at over 0.1 degrees Celsius. And this is also translated into the aviation's share of global remaining carbon budget by 2050. And then we are comparing the warming to date of 1.36 degrees to a 1.7 degree budget. And then in the historical trends and current commitment scenarios, you will see that there's a quadrupling of aviation's share of the global carbon budget. And then if we look at the GHG forward scenario, it will be able to have aviation's warming contribution to only 89 millidegrees Celsius, but it still doubles aviation's share of the remaining carbon budget. And then when we add on, when we look at the SLCP forward scenario, we'll see that the mitigation potential from non-CO2 climate pollutants it will be able to cut 2050 warming level by 3/4 compared to historical trends. But there will be an inflection point around 2043 where the continued accumulation of CO2 in the system overpowers the near-term cooling trends from SLCP controls. This is highlighting that if we only focus on SLCP mitigation, there will most likely be a return to the warming trend beyond 2050. And then only in the full breakthrough scenario where we combine aggressive GHG and SLCP mitigations, we can see a stabilization trend around 2050, where the warming contribution from aviation is cut by 90% compared to historical trends. And then aviation would only take up 2% of the remaining 1.7 degree global carbon budget. And here is the table reiterating the alignment of different scenarios to the climate budgets. So in the 1.7 degree Celsius scenario, as I said, there's we go from quadrupling to doubling to a halving of aviation's share of the global budget. And then what's worth noting is that in the full breakthrough scenario, we can also keep aviation's share to the 4% that we're seeing today, in under the 1.5 degrees Celsius scenario. This is only 0.1, there's only 0.14 degree left in this particular temperature scenario. And in terms of the contribution from different pollutants to the total warming impacts from aviation, we are showing you the per species warming contribution from the highest contribution to the lowest contribution, including cooling contribution from sulfur. And then I would like to remind everyone that the four pollutants on the right are on a different y-axis scale, which is 7 times smaller than the y-axis magnitude for CO2, contrail, and NOx. And then I think the key trend here is that most of the avoidable warming is really driven by contrail mitigation, where it's for the full breakthrough scenario, it's about 0.04 degrees of reduction. And then there's only 0.1, about 0.01 degree of warming reduction from CO2. And then this is just really linked to how CO2 keeps accumulating in the atmosphere. So even if we maximizes our mitigation technologies, it will not be translated into reduced warming that quickly. And then contrails are sort of the opposite, where we'll see very immediate effects of reduced warming. And the last key results that we wanted to highlight today is how the avoidable warming in the full breakthrough scenario distributes across different mitigation levers. And you will see here that contrail avoidance dominates the avoidable warming in this scenario at over 40%. It's followed by SAF at 20% and hydrotreatment and operational efficiencies both at around 10%. These top four levers combined will contribute about 90% of the avoidable warming in this scenario. And then I think two key trends here is one is that SAF, you will notice, have equally significant contributions in GHG, reduced GHG warming and reduced SLCP driven warming. And it's really highlighting the double benefits of investing in SAF. And the other note is that even though lean engines and technical efficiency improvements from airframes are not ranked very high in this table, it doesn't mean that they are not important technologies. They are very much uh, critical to long-term GHG reductions. I think this table is really serving the role of highlighting what are the more near-term opportunities in terms of stabilizing aviation's climate contribution by 2050. And lastly, I will just walk you through a few high-level takeaways based on the results that I just shared. So first of all, as I mentioned, aviation will double its contribution to global warming under a business as usual scenario. It will also quadruple its share of a Paris compatible climate budget. And with maximum greenhouse gas emissions reductions, we will be able to cut the warming contribution by half in 2050. But the aviation's share of the climate budget will still double in that case. And in the SLCP forward scenario, we see the power of with the near term, the power of reducing near-term warming using different SLCP control measures and with control avoidance being the most dominant lever in this scenario. But the inflection point around 2040 and then the likelihood of continued warming from CO2 is also a very important trend from the scenario. This highlights that only combined GHG and SLCP mitigation actions will help us get on the path of climate neutrality after 2035, and then achieving the 90% cut in warming 2050, but also keeping it that way post 2050. And lastly, there's in terms of which technologies to prioritize, we think policymakers should really adopt SLCP controls as soon as possible while continuing to develop the long-term GHG mitigation technologies in the meantime. And that's all from the summary presentation.
All right, great. Thank you very much, Sola. Great presentation. So I'd like to do a quick discussion section now where we bring in our other two presenters. Quick reminder, if you do have questions about the study, please put them in the Q&A panel. We'll double back to those at the end of the session here. So keep those questions coming in. Just to pick off one quick question. So from Yorkham, good to see you, Yorkham. Your question was, which of the 5 modeled scenarios is the closest to the direction we're currently going right now? By definition, we designed the current commitments scenario to try and capture existing policies and then existing industry goals on fuel efficiency. So by definition, the current commitments is our best read of where we're going right now. And as a reminder, under the current commitments trajectory, we expect that aviation would consume about 15% of our remaining temperature budget under a well below 2-degree scenario. So that's roughly quadrupling aviation's historical contribution of warming to date, which is about 4%. But thank you for your question. Before we jump into the Q&A, I'd like to spend a little bit more time digging into the specific findings about short-lived climate pollutants. As Sola just introduced, we find that SLCP control could contribute about 85% of all avoided aviation warming in 2050. So it's a major new lever identified in the study. So of that, the largest potential contributor is contrail avoidance. So I'd like to bring in Giant to talk a little bit about contrail mitigation in particular. So Giant, governments and industry have been relatively slow to embrace contrail mitigation, in part because some have argued that the uncertainty still remains too high. Please talk a little bit about how we quantified contrail uncertainty in this study, and specifically, please relate that to the debate about CO2 versus contrail warming trade-offs. Those can occur when planes are rerouted to avoid contrails and then take less fuel-efficient flight altitudes.
Thank you for that question, Dan. One thing to just say at the outset that the climate impact of contrails will always be more uncertain than the climate impact of CO2. This has been true for the past 2 decades and will likely stay true for any relevant time horizon. But that doesn't mean we've not made any progress. What recent research has changed in the last few years is that we have been able to gather new lines of evidence using different modeling and observation tools that show that contrails are warming and provide a best estimate for the magnitude of that warming. For this study, we combined 18 estimates across 12 papers that use 9 different methods to make one estimate for 2023. And along with that, we do a rigorous propagation of uncertainties and present the 95% confidence interval of what that estimate should be. And what we find is, despite the uncertainty, it still makes sense to practice contrail avoidance. 33 to 1. That is how much the climate benefit of avoided contrails outweigh the climate cost of additional CO2, according to our best estimate. And now, even if contrail impact is 5 times smaller than that estimate, which is the lower bound of our 95% confidence interval, the climate benefits still outweigh the cost by 10 to 1. That for us pretty much closes the debate on whether avoidance is a net beneficial for the net beneficial for the environment, and gives us the confidence to say that contrail avoidance is really a no regrets solution, and that the technology should be progressed through larger scale demonstrations.
Okay, great. Thanks, Giant. Related to that question, one of the big revelations from me from the study is that flights departing the US and Europe are responsible for about 2/3 of contrail warming. Can you say a bit more about what are the drivers of that finding and also what policy implications it holds?
Mhm. Yes, some of that can be attributed purely to differences in the level of air traffic. US and Europe are some of the highest air traffic areas, but some of it is attributed to really macro Earth scale weather patterns. So these contrail conducive areas occur at the edge of the troposphere and the stratosphere. And there is most overlap with that region with cruise altitudes at higher latitudes. So think 45 degrees latitude or higher. Now, other phenomenon like Hadley cells, which is a Earth scale circulation, results in more humid air in the upper atmosphere near the equator than in the subtropics. So there's this dehydrating of the air in the subtropics, leading to less contrail formation in those areas. These are latitudes that will coincide with areas like India, China, and also Mexico. And then there is also a large amount of warming that's happening in the upper latitudes, and that is more coincides with the US, Europe, and the North Atlantic. And so really what this means is a majority of the warming can be tackled through cooperation between a few countries, and specifically countries in the literal and figurative global north. That bilateral cooperation across the North Atlantic between the UK and Canada, countries responsible for the airspaces over the North Atlantic, would be a really good start.
Okay, great. Thank you, Giant. Let's turn now to fuel composition, which is also another important lever in our roadmap. So, Supraja, this is a question for you. So fuel composition is front and center in most net zero CO2 roadmaps, but as sustainable aviation fuel. In this study, we also investigated hydrotreating of fossil jet fuel as a mitigation lever to reduce contrail warming. How does hydrotreating work, and what's the scientific or physical mechanism by which it could reduce contrail warming?
Thanks, Dan. So hydrotreating is a refinery process that removes the impurities from fuels using mostly hydrogen plus some other catalysts. And it's an already mature technology that's used across refineries, but right now there's a pretty wide range of jet fuel compositions that exist depending on the specific refinery we're talking about and the region. And looking at it from an emissions perspective, hydrotreating is able to remove or reduce compounds like aromatics, sulfur, and naphthalenes, and these contribute directly to the formation of particulate matter in the combustion process. And particulate matter emissions during the cruise phase contribute directly to contrail formation by acting as what we call condensation nuclei. And these are basically just surfaces for water vapor to freeze and form ice crystals and then eventually turn into contrails. So the non-CO2 benefits of fuel composition really remain the same regardless of whether we're talking about fossil jet fuel or SAF. So this means that as SAF production scales up and increases, hydroprocessing or hydrotreating fossil jet fuel could be a good interim strategy to maximize all the non-CO2 benefits that we could get from fuels.
Okay, great. Thank you, Supraja. Let's turn to engine emissions. As we noted earlier, there are some sort of classic air pollutants released from aircraft engines, which also have a climate impact. So here we're talking about emissions of nitrogen oxides during cruise, and then also fine particulate matter, or NVPM, that's linked to contrail formation. What's your assessment of the potential for new engine technologies to reduce these types of warming? And then also say a few words about what policies might accelerate the development and uptake of these advanced engines.
Sure, yeah. So engine technology development from the industry perspective, I'd say, is largely tied to maximizing fuel burn reductions or CO2 reductions. And there is a trade-off with NOx and particulate matter coming from that. But over the past 2 decades, I'd say we've seen some new technologies coming into service that also have large NOx and PM reductions, these being engines using lean burn combustion technology. And lean burn combustion is a promising way forward for achieving reductions in NVPM and NOx emissions, and we're seeing them become a larger part of the global fleet. On the policy side, right now at ICAO, there is a new NOx stringency that's being developed, and this process will continue over the next 3 years. And I'd say if it's sufficiently stringent, the standard could accelerate the development of new low NOx combustor technologies. But we have to remember that new engine introduction takes time to penetrate the fleet. So impacts across the fleet and through 2050 would take some time to see. And then on the PM side, there aren't any new engine standards that are being developed in the near future. So the main policy mechanisms for PM reductions would have to be through fuels, as we discussed with hydrotreatment.
Okay, great. Thanks so much. In the interest of time, let's move to the question and answer session. So just a reminder, you should have a panel on your Zoom, which allows you to pose questions. So please keep them coming. I'm seeing a number of excellent questions here, and we're running the gambit from non-durable carbon removal all the way to permanent geological storage. So we've certainly got a breadth of good questions here. I see a couple of questions related to the abatement costs of contrail avoidance. and how we modeled those in the study. So maybe Giant, can I put you on the spot for that?
Yes. So in this study, we compared, we only really quantified the cost of SAF, hydrotreating, and the additional fuel burn from contrail avoidance. And in that comparison, contrail avoidance kind of wins out with being the most cost effective in a dollar per degree Celsius abated. Uh, that is followed by hydrotreating and then finally by SAF. So, and in terms of magnitude of cost, contrails are about twice as cost effective as hydrotreating, and hydrotreating is about 17 times as cost effective as SAF. So the difference between the cost effectiveness of SAF and contrails is on the order of 34 times.
Okay, thank you. Another question for you, Giant. Comes from James. He notes that we've modeled breakthroughs in alternative jet fuels and contrail avoidance, but he's curious if we have modeled a breakthrough in electric and hydrogen aircraft. I know this is something that you've led across both studies. So yeah, can you talk a little bit how we have modeled the potential benefits of zero emission planes in 2050?
This is a big change from our previous report that did assume, at the time we were working on timelines that were current for Airbus, suggesting they would have a narrow body hydrogen powered aircraft in 2035, entering service into 2035. In the past few years, that has been delayed with the reality of developing new engines coming into view, and also electric aircraft startups have had difficulty in really commercializing their products. And so keeping that in mind, we had to push back the timelines for these hydrogen and electric aircraft. So we aren't necessarily modeling a breakthrough in those technologies. We do expect them to be entering later than we were 3 years ago.
Okay. I recall from our 2022 study that we started to introduce hydrogen aircraft around 2035. By 2050, in our breakthrough scenario, I think they were responsible for about, 21% of fuel use in 2050. Do you recall where it is now in this new study? What share of 2050 energy use is from hydrogen aircraft?
Not off the top of my head, but it'll be below 1%.
Okay. Yeah, so the delay in the aircraft development is really biting at this point when you think about 2050 and the time it takes to mature the technology and especially roll it into the fleet. So unfortunate development these days. So we've got a couple questions about residual emissions, I would say, and also incentives for contrail abatement. So the first one, well, let's do the short-term question here. As we know, there is a significant interest in industry about carbon dioxide offsets and using that as a way to mitigate it and emissions today while we scale SAFs and other long-term technologies. There's also a debate now about whether you could develop some sort of offset system for contrails. In essence, have an offset market as a way to incentivize contrail avoidance. So kind of a tricky one. Giant, I think this goes back to you here. There's obviously a difference between temporary carbon removals that only keep CO2 out of the atmosphere a few decades, like forestry. You've got contrail avoidance, which provides its benefits over the timescales of hours to days. And then you have CO2, which is close to permanent in the atmosphere. So you're kind of our contrails guru. Have you given much thought to how you might design policies that don't avoid perverse incentives across these three timescales and kind of promote the technologies that we need?
Yes. Comparing contrail avoidance to permanence is interesting. And there was a recent talk that had gone to where Piers Foster, a climate scientist, had suggested that for contrails, contrail benefits to be permanent, you have to be doing contrail avoidance from now until forever. Like that's what it means for contrail avoidance to be permanent. And in that sense, you can get that if airlines do incorporate contrail avoidance in sort of their daily day-to-day flight planning procedures, and you avoid it like you avoid thunderstorms now. So there is a pathway to having contrail avoidance be a permanent reduction in the temperature, but it does require airlines to commit to doing this for the foreseeable future. We do not want to be incentivizing contrail avoidance at the expense of CO2 measures, because in the long term, if we only do contrail avoidance, yes, we get those short-term reductions in the temperature response, but the accumulated CO2 in that time continues to warm the environment, and any short-term gains that we make from from SLCP mitigation now will be overrun by warming from CO2. So really, we need to be acting on both, and that's what the full breakthrough scenario is suggesting is the only way to reach that climate neutral goal.
Okay, thanks, Jai. So on the flip side, we have a question about permanent removals. And Sola, let me pose that to you. So as we've discussed, basically in all of the scenarios, we are seeing significant residual emissions in 2050. So the question here from Yash is, does it make sense for stakeholders to invest in engineered removals? So carbon dioxide removal, biomass and carbon sequestration, and/or biochar, to avoid a potential situation where operators are stuck between high carbon prices on the one hand and then very expensive removals on the other?
Yeah, thanks, Dan. I think that's a very interesting question where ICCT modeling has always been more in sector. And I think one key trend is that the large amount of ESAF that's present in our modeling also ideally requires carbon captured, like direct air capture or other type of carbon removal related adjacent technologies. So it really poses the question of if we were able to scale up removal, then will we prefer direct removal or using it for SAF? And so that is definitely an ongoing kind of open research question that's on our mind as well. I think there are some concerns about how removal, if it's not done fast enough, it wouldn't deliver as much climate benefit as we think it would. So like this relates back to how cumulative CO2 and other greenhouse gas emissions would like how it works in terms of overall temperature contributions. So I think there's more work to be done in like figuring out whether how we balance the development of SAF, which is also really expensive, versus the other removal technologies.
Okay, great. Thanks, Sola. I'm seeing a few questions that have been answered directly in the chat, so thank you for doing that. Please keep your questions going. We've got a few more minutes, but so Supraja, maybe it's time for, I think it's time for some magical thinking here. If you had a magic wand and you could compel the aviation industry to mature and deploy one single mitigation technology or practice, what would that be?
Interesting question. I think based on our results, I would say the obvious answer would be contrail avoidance, but I'm going to pick SAF on this one because cost and scale up wise, I think SAF is more complicated and expensive than avoidance, or at least that's what our results are showing. So I would use my magic wand to deploy all the SAF that we need, and then we can work on avoidance trials, continue developing humidity sensors, and wide-scale deployment of contrail avoidance without the magic.
Okay, thank you. We are seeing some new questions here. One is related to decarbonizing conventional Jet A production as a bridge strategy. And again, we're talking here about the evidence showing that SAF deployment is a little bit behind. So, Supraja, I guess is a question for you. Do you see a future in which renewable energy in refineries is used to cut upstream emissions as part of the fuel production process? And maybe you can relate this as well back to the discussion of hydrotreating, because I think the potential use of green hydrogen for hydrotreating is something that we're also looking into.
Yeah, sure. So in terms of just fossil jet fuel and upscale emissions at the refinery, I think that's definitely a strategy that could be pursued with additional renewables if and when they are available, not taking away from decarbonizing other sectors. And on the hydrotreatment side, when we modeled the additional emissions that would occur at the refinery from hydrotreatment, that's about 3 to 4%. We saw that even with those additional refinery level emissions, the SLCP benefits that we get outweigh that cost. And in our modeling, it was purely climate benefits. So if we also add in the local air quality benefits that you would get from lower SOx emissions and lower particulate matter emissions, we think that that would outweigh the added refinery emissions.
Okay, great. Thank you, Supraja. And I see a few questions being answered in the live chat. I think we have time for one last question. It is related to the codependence of technologies like direct air capture, green hydrogen, and then also the production of e-kerosene. So I think the specific question is here, to what extent did we model feedback loops in technological learning between those various technologies in the studies? And I think this probably relates to the cost assumptions that we're using for those technologies. But Sola, can I ask you to weigh in on that?
Sure, but I think the short answer in terms of modeling is that we're not modeling the technology dependencies or like the learning curves that can be shared among various like a few different levers. But I think yes, indeed that there is a lot of I think implications from our modeling where like green hydrogen is needed for multiple levers, and direct air capture is needed for multiple levers as well. So I think what we do model is that ESAF will come down in cost over time due to both kind of climbing the learning curve of the technology itself, but also economies of scale, which is not kind of applicable to the biofuel side, where feedstock cost is the main driver of the cost. So I think it is incorporated kind of on a blanket level in our cost assumptions, but I think that we'll need to look at more in the future into the dependencies that you're describing. Yeah.
Okay, great. Thanks, Sola. I'd like to close with just one final thought. And again, Sola, this is coming to you since you're the lead author of the study. In your mind, what's one key takeaway from the report that you would want people to remember from today?
Yeah, I think I want to highlight that near-term potential, like there is a lot of near-term potential from SLCP mitigation, but we will definitely still need the greenhouse gas mitigation in the long term. So it is really a two-sided coin that we have to not ignore either side of those. Yeah.
Okay. And if I'm correct, we have a blog post that will be coming out soon that explores this issue, right? In essence, extends the modeling from 2050 out to 2100 and shows the importance of continued action on greenhouse gases as well, correct?
Yes, we're working on a more simplified, but I think very important analysis of the 2100 timescale. Okay,
great. All right. Well, I think we've answered the questions we can today. So thank you for sending those in. Thanks to all of our presenters today for their excellent comments. And thank you to all of the participants who dialed in for the presentation. Please feel free to reach out to us if you have additional questions. If you look in the chat, you'll also see some additional information, including a link to our various social media accounts. There's also a monthly newsletter called Clean Ascent that you can subscribe to. So please do so if you would like to get more information about ICCT's aviation program and our research. So again, thanks to everyone for dialing in, and we hope to see you again soon.